Let's discuss another application for a gravitational field strength due to a circular arc. Say we are given with a uniform rod which is bent in the form of a circular arc like this, and say the arc is subtending an angle phi at its center, and say we are required to find the gravitational field strength at the center of curvature of this arc, and say we are also given with the radius of curvature of the arc which is r. Say if its mass is m. To find out the gravitational field at center, we consider an element which is located at an angular separation theta from the angle bisector like this which I am drawing, and say this element is having a width r d theta. For the complete rod, if mass is m, for this element we can easily get the value of its mass as m upon the total length can be written as r phi, as phi is the total subtended angle by rod at center. So length of the rod is r phi. So m by r phi multiplied by r d theta will be the mass of this element, which can be written as m by phi into d theta. Now, due to this element, we can see the gravitational field at the center will be along the direction of this elemental mass dm, and say it is dg. So, we can say if dg be the gravitational field strength due to elemental mass dm, then we can use dg is equals to g dm by r square, as due to a point mass the gravitational field is gm by r square. And in the situation of this dg, it will be having two components. One is along the angle bisector, which is dg cos theta, and other is perpendicular to the bisector, which is dg sin theta. And in this situation we can state, when we integrate the element from one end of rod to the other, along the angle bisector, its net component, all the components will be added up, which is dg cos theta and dg sin theta will all get cancelled out, because corresponding to each segment on right of the bisector, there exists a segment on left corresponding to which dg sin theta will be opposite, and these two components will cancel. So we can write net gravitational field at point C is g at C can be written as integration of dg cos theta, and if we substitute the value of dg, it will be g dm. I can substitute as m by phi r square d theta multiplied by cos theta, and for the angle theta it will vary from minus phi by 2 to plus phi by 2, which I need to integrate. For the whole rod it will be minus phi by 2 to plus phi by 2. So on integrating, I will get the value of gravitational field at center as this gm by phi r square as a constant. I will take it out, and will be having integration of cos theta d theta from minus phi by 2 to plus phi by 2. So on integrating, we are going to get this is gm by phi r square. Integration of cos theta is sin theta, and we apply limits from minus phi by 2 to plus phi by 2. And on simplifying, it is sin phi by 2 minus of minus sin phi by 2. It will be 2 sin phi by 2. So the result will be 2 gm sin phi by 2 upon phi r square. This is the gravitational field at center due to the circular arc. So just keep the result also on your tips, because there are many applications in which we are going to directly use this expression.